Hey, recording and rolling. Welcome to Friday, September 29th. Do you guys turn in your chapter 4 or 5 puzzles? A lot of you guys already turned this in because we did finish covering them in class a couple days back, I think, right? So, yeah, so those are due today, chapter 4 or 5 puzzles. You guys remember your Forces take home quiz is due Monday. I've got some last demos for you guys today. We're going to wrap up this unit today, Forces, Newton's laws, sort of thing, right? And then I've got a small Bible, guys. So one thing at a time here. I flip my screen over, show you guys this video demo that I never got to yet. All right. Have you guys ever seen this where if you hold a slinky and drop it? You guys ever tried this? What do you think's gonna happen? You drop a slinky. Aha! Right, right. Check this out. Ooh, look at that. Whoa! Great! Whoa! 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 All right, so different okay, so explanation for this, perspective on this. All right, so suppose you looked at a free body diagram of just like one point on the slinky. Let's say a point near the bottom, right? Like some little small segment of mass. Right? Well, at this point, it would have two forces on it. It's got the weight acting down, which might be like like less than a gram or something. You're talking about a little tiny segment of mass, right? And it's got the tension force pulling up. Ooh, okay, so weight down, tension up, right? And that's going to be in equilibrium until, until that tension force goes away. But it looks like it takes some time. Like there's a time delay for that tension to go away, right? And this right here, the slinky drop, might say something about the wider universe, right? The fact that there's a time delay for that information to reach it, right? It doesn't just fall right away, right? Uh, so do you guys know the limiting speed of anything in the universe? What's the limiting speed? The speed of light. Yes, the speed of light, right? Okay, which is not exactly what's going on here, but maybe it's somewhat related, right? So let's say NASA sends a space probe to Mars when they're trying to communicate with it. Okay, we got to make it turn left and like pick up that rock. Okay, can that signal reach Mars immediately? No, it's going to take a few minutes, right? A few minutes delay. And then it's going to take another few minutes for the space probe to send back the info from the camera saying, okay, yeah, we did in fact pick up the rock, right? Okay. So what about like everyday materials though? Or how about just like you hearing me right now, hearing my voice? Do you think there's a tiny, tiny delay between my voice and you hearing it? Yeah, because there's a spatial difference, right? It takes there's a speed of sound, right? Speed of sound for say like vibrations to go through the air. That's actually more closely related to what you guys are seeing right here, right? So like any materials, like if there's a pen on your desk and you pick up the pen, right, the location we're picking up actually moves a little bit faster than say like the opposite end of the pen, right? Because there's like a spatial difference between the two ends of the pen, right? But your pen you could think of as like a really really stiff spring versus a slinky is maybe not so stiff, right? All materials have a spring like quality to them, right? You press or pull on some object and it's going to respond by compressing or stretching itself at least a little bit, right? And the slinky is just like a spring with a really small spring constant. But how about like a concrete block? Concrete block could also be like a spring, just with an enormously high spring constant, right? And the slinky would be enormously low spring constant. So you really see these effects play out where there's this time delay for that information to travel. Ooh, so that is pretty cool looking. While I got demos rolling, another demo also from the same YouTube channel here. It's called Veritasium. Here's a cool one. He's got a couple of videos related to something called the Magnus effect. You guys ever play sports and have a ball like spin and then therefore start curving? Right? Like how does a curve ball in baseball curve? Or maybe if you played soccer, like you can put spin on the soccer ball and like curve around, maybe go into a goal. Right? Now, if you just drop the ball straight down, it goes pretty much straight down. Maybe it's being pushed around a little bit by the air, right? So not straight down. Well, if you spin this thing, now what? Whoa! What's going on there? Yeah, that's just like a crazy curveball. Right? It's curveball. Right, so here, I just got an explanation for this. Okay. Let's see that again. Veritasium is the YouTube channel. Let's see this. Okay. Let's do a little ball. Okay, here we go. All right. Magnus effect. Right, so curveballs, the whole deal. Right. So we have like a spinning ball, right? It'll like push the air around it, right? And then there's a pressure differential. And that pressure differential You guys remember pressure times area results in a force. That'll like force it a certain direction. All right, so that one's pretty fun. Let's bring this back over here. All right, but how about back to like those slinkies and those springs, right? So we actually started this whole unit. I gave you guys a bunch of spring scales, and I gave you guys like 10 mini labs. You guys remember that? And I keep referring back to those 10 mini labs for a bunch of things we've been doing. Okay? So the principle by which these spring scales are operating is this Hooke's law, right? F equals kx. You put some force on the spring scale, and it's going to stretch by some amount x, right? Or some textbooks have a negative here because they look at the this responding force, right? Right. So F is how much force, X is how much it stretches in this case, because the spring scales just stretch, right? Although you could compress the spring in general, but these are stretching. Okay? Now K is how stiff the spring is. It's called the spring constant, right? Which is like the slope of this line, right? So right, maybe not very stiff could be like this. This could be like a slinky. This could be like a concrete block, right? And then these spring scales are like somewhere in the middle, right? There are 6 different spring scales, and they should be on your desk. You guys see 6 different color spring scales? I have them ordered here. Blue, green, brown, red, white, gold. That goes from the least stiff to the most stiff. I'll have 3 of those up here. But you guys also have a quarter page on your desk. You guys see that blank quarter page? All right, this is going to be the lab that's going to close out this whole unit. And then on Monday, we'll start something new. Monday, we're going to start like a combination of things we're going to put together. We'll put centripetal force and gravitation and make orbits. So, okay. All right, a little bit of circular motion. All right, for today, put your name on your paper. Name. All right, so you guys got your name on your paper? Let's call this spring constant lab. Spring constants lab. Okay. Go ahead and copy down this right here. Okay. I'll do it with you guys. I'll do the same thing. So what's the spring constant for the blue spring? Right, this blue spring. Wonder how stiff is this spring? Okay. What's the spring constant for the green spring is the next one. What's the spring constant for the brown spring, which is like the middle one? Okay. Ooh, that feels a little bit stiffer. Ooh, takes a bit more force to stretch that one. Okay. What's the spring constant for the red spring? What's the spring constant for the white spring? And what's the spring constant for the gold spring scale? Oh, and I have the gold one here too. Okay. Oh, this is like the stiffest one you should have. So, right. Ooh, takes a lot of force. A lot of force. Ooh, it's really hard to stretch that. Takes a lot of force. Right. So how can we quantify that? So I'll say equals. Right. Hey, what do you guys think the unit would be for spring constant? What do you think the unit would be? How do you go from meters to newtons? You have to multiply by. You have to multiply in the newtons and divide by the meters, right? That'd be some number of Newton per meter, right? So take some number of meters, stretch, multiply by Newton per meter. That gives you newtons, right? Makes sense? Oh, that's what I have here. Okay. So some number of Newton per meter. Here, I'll do an example with you guys. Let's say the gold one. Let's go for the gold. Yeah, gold. Okay, so I'm gonna put some force on this. Let's say like 30 newtons right there. 30 newtons. 30 newtons of force. How much did that stretch? Well, it stretched this one. Hey, I have a ruler. You can see how much it stretched for those 30 newtons. That is, oops, zero that out. Like 3.7 centimeters. It looks like 3.7 centimeters. 3.7 centimeters, right? So I'll do a math on the back of that. So I know Hooke's law, F equals kx. The question here is, what is the spring constant? Okay. Hey, we can solve in terms of variables a little bit, right? Can you guys say k is f over x in terms of variables? That's just a little algebra stuff, just in terms of variables. That's all right. Okay. Now let's say spring constant for the gold spring. Okay. Well, I pulled with 30 newtons of force. Pow, that's that number right there. Okay. And it stretched, it was 3.7 centimeters. Ooh, but guys, if I want units of Newton per meter is what I want. Okay? Guys, how many meters is 3.7 centimeters?
0.37 or 0.37.
There you go. Yeah. 0.037 meters it is, right? Because, well, how many cents in a dollar? 100, right? So centi is 1/100th because that's 2 decimal places. Guessing 3.7 centimeters would be 0.037 meters. Same thing. Okay. Maybe I'll make a note over here. Right. 3.7 centimeters equals 0.037 meters. All right, this little thought bubble over here about that. Okay. Okay, so all you gotta do is divide that, and that'll tell me how many newtons per meter is the stiffness of the spring. And this should be the stiffest one, so this should be the largest value spring constant on your lab here. All right, so 30 newtons and 0.037 meters. All right, that is it's like 811. That would be Newton per meter. 811 Newton per meter. That would be. Okay. Okay. You guys got that? All right. Do you guys think you can figure out the spring constant for? Okay. Oh, okay. So here to go to the front here. So I got 811 Newton per meter. Just like that. Okay. You guys think you can figure out the spring constants for each of the other springs? Okay. When you do, go ahead and pop that in the grade tray. Okay. Got a short day today. Walk around and help you guys out. You guys remember you got a take-home quiz due on Monday, right? If you got a few spare minutes in the class, you got that, right? Some students who didn't take home the rest of the class to figure this out. Right. Also got here, got some books out on this test. So if you really got nothing better to do, right? Got some fine books right there. You guys can borrow for a few minutes.